As was mentioned in the introductory video, the move optimal algorithm for a single Dutch flip for this move set is 29 moves, and in this video I'm going to derive a 37. It's perfectly understandable. You'll really like this one. This one is based on a piece isolating commutator, and that is this right here, this 3-cycle. I'm going to explain this 3-cycle now. Notice this right here, this x in this piece isolating commutator xy is a conjugate of the move r2. That is, if I start out with r2. Now let's suppose, just experiment, I have to do 3dw, or 3dw prime or 3dw2. That's the only way. If I start with r2 and I want to conjugate, that's the only moves that I can do. So I invert it with 3dw prime. Now we have some pieces in the right and the left half of the cube, and they're kind of getting out of the R slice. That's what I kind of want to do. I kind of want to get pieces out of the R slice as much as possible. So let's cheat. Let's take a look at the next set of moves for this conjugate, for the x part of the piece isolating commutator xy, R and R prime. If I just move this 1x4 block down, that's what this R prime at the end means, as I've been saying. It's also going to mess up this x center as well. It's going to move that up here, but as you can see, and this is solved, but it moved that there. But look real closely at this. Pretty much most of the pieces are confined now into the front half of the cube. And since I'm allowed to move all of the bottom layers, it's going to get all of these into the left half of the cube with a 3dw move set up to this, and 3dw prime to undo. It's going to move all that there. All that's left is a single wing edge. So from this point, we can create a piece isolating commutator 3-cycle of wing edges. What I'm first going to do is expand this now. Now, I'm going to take this 3-cycle and I'm going to put it over here for right now. Recall with the first 2-gen algorithm with lowercase r and capital U turns only, we had the move sequence r, u2, times 4, and then r. And that created this. So does a similar repeated sequence exist for this type of 2-gen? Well, let's take a look. If I just convert this to dw, instead of u, because I'm using d, as I mentioned before, and then r, will that work? And it gives us something interesting, but it's still quite not completed centers like that one was. If I just remove this and observe this in here, I notice that the largest cycle seems to be 1, 2, 3, 4, 5, 6, 7. This one is 1, 2, 3, 4, 5, 6, 7, which is of equal length. And then I see 2 cycles otherwise. So maybe if I repeat this 7 times to beat the largest cycle, and 7 is odd and 2 is even, so the 2 cycles are going to stay, what will happen? I have this, which looks pretty nice. Maybe if I added a, let's say, 3dw2 turn to it, whoa, look at that. So it looks like 7 might be the number for this type of 2-gen. Now using this repeated sequence, we will be able to derive a 46 move single Dutch flip algorithm. I will get to the 37 directly afterwards, but that one's a little bit more unobvious, but here we go. First note that if you've never seen this before, if you have 2 opposite centers in which on the supercube they're pretty much straight up, that with an E2 turn, the centers are going to be perfectly solved on both sides. If you've never seen this before, it's a little bit unobvious. But from this point, if I were just to conjugate this with an R2 and undo that, then it won't discolor those centers anymore. But with this move sequence, you see we have a problem here and here. So let's go back and take a look at the supercube, the top and bottom faces. Now look at this. The bottom one is rotated 180 degrees. We have to somehow counteract that. The top is perfectly fine. But the bottom, we have to somehow counteract that like we did with the previous 2-gen. So let me put this aside. And this is type 2-gen. I'm sorry, I didn't relabel that. I'm going to put this here. So this is another move sequence that we have in our tool chest. Another one is, well, let me see. What about PLO parity? does a PLO parity exist on here? If we do R2 3DW2, R2 3DW2, and R2, will that work? Look at this. It moves it in the bottom, which is exactly what we need. We need the bottom to be rotated back 180 degrees. But if we look at our 4-cycle move sequence here, it involves all the pieces in the M layer. If we were to use a PLO parity algorithm just for the sole purpose of correcting this center here so that we can do some conjugation, and as I've shown before, the reason why is if we do an R2 setup move to this, yes, it will not discolor the front and back centers anymore, but now the top and bottom are messed up. That's because one of these, at least one, if one of these is rotated 180 degrees and you conjugate it like that, it's going to slice through it and break it up. In order to not break it up, they should be not rotated 180 degrees at all. So because of that, I have to somehow temporarily fix this and then undo it at the end. And we can do this with PLO parity. We just have to get these dedges out of M somehow. Since we're using a 3DW2 move anyway, watch what happens. If we, let's say, conjugate with 3DW, just a quarter turn of DW and then DW prime, what will happen? All of that will be out of the F and B and M faces entirely except for this 180 degree rotation of the bottom center. Now, with all that in mind, I'm going to keep this algorithm piece handy. Let me put back the other sequence here. I apply it to the cube. It may not be initially obvious, but if I just take this, because it can be, without it, this is just a 3DW2 from being pretty much restored as much as possible at the current state. If I would just move it to the beginning, this is actually the derivation for this algorithm. It really makes no difference. We have this. And now I take a look at the 3-cycle that I derived previously with a piece isolating commutator separately. If I just take this and I conjugate it with R prime, so that I basically take these two wing edges and move them into the top layer. So I'll do that. So I need to move them. The end result needs to be they need to move up. In order to do that, I need to have the inverse of that as the first setup move, and this is the undoing of that setup move. If I look back, this is just basic parity algorithms from anybody who were to make parity algorithms without knowing anything that I've described in my videos is pretty much the process. So I'm sure many will understand this, can play around with this. If I just take this temporarily and just look at this, I have a wing edge here and I also have some here, so it kind of matches. So you have to play with it a little bit, but when you do, all of a sudden I get, and that's why it was a little obvious that I put this here, but I experimented some, and I have two wing edges oppositely like this. So from this point, I would be really tempted to do a R2 move to make a single dedge flip. And it also fixes back the front and back centers, but it discolors these. So this goes to what I was talking about with the PLO parity algorithm. If I would just first, before I do that, I would take the PLO parity, which was this, so that I rotate that bottom composite center first, so that it's perfectly solved. That way when I do a setup move slice through M, it's not going to break up any additional centers. That's a really cool trick. It's going to cost some moves, but it forces you to be able to get what you want to get. So now I have a single dedge flip. All that's left now is this PLO parity in the L and R slices, which I simply take the same PLO parity to undo what it did, because I only use it to rotate this composite center. That's the only reason why I use it, so I have to undo it. And now I have a single dedge flip. And it's in the bottom, but this is using 3DW turns. So in the 2gen 3UW and lowercase r moveset, this is going to be in the top. And so this is going to be, with my program for canceling moves, I didn't do a few things. So for example, I didn't have it deal with repeats, even though that would be quite easy. So I'm just going to simply multiply this by 7. In addition, I'm just going to go to Notepad++ and replace all 3Ds with just D and copy it and run it in my program. and it gives us a 44 move algorithm. I'm going to back substitute a D with a 3D, and we're going to take a look at it in the Cube Simulator Cube Twister. And there you go, it's a 44 move algorithm. Now I'm going to show you a process that I used to find at 37, and so that's that. Now this doesn't translate to the higher order cubes as far as I know, but the next one will. Let's go take a look at that. To start out with, if we go to the 4x4 Parity Algorithms page at Speed Solving Wiki, the shortest 2-gen algorithm sequence, that's a 4 cycle or an odd permutation, just like what we used for the other one. We start with a 4 cycle. We have this one. Well, if we just convert these RWs to lowercase r's, then we have 2-gen. And these U2s in this 2-gen will not be U2, it'll be 3DW2, but let's observe what happens if we were to apply this move sequence. So besides this 3 cycle, and I didn't write it out, but what we used before, we had the R3DW2 times 7, and then I put the 3DW2 in front. This is another move sequence that we have in our tool chest. We will have R2, 3DW2, and then let's say, like, we could use either R or R prime, but for this derivation I'm going to use R prime, so that's why I'm writing R prime, right, R2. Well, wow, look at this. It looks almost like if we were to apply this algorithm to the cube, it looks like this. So basically it's the same thing, but it's in the bottom layer, but it's in the moveset of our desire. Now the first thing I need to do is I need to adjust this so that the majority of this is in the right half of the cube. The easiest way to do that is just with a 3DW2 move for setup. I have that there. So I'm going to write this here, and I'm just going to label this Waterman. So this is another algorithm piece in our tool chest. From this point, I know it might be a little bit unobvious, but if I were to do an R2 move, this was done by experimentation, then I have something that looks like this. If I conjugate this with R prime, and I undo with R, that's going to move all this away from me. Look at this. It pairs up this dedge here, doesn't it? Very, very interesting. Now, if we go back to, and I didn't have this in our tool just as well, but the PLO parity, which is pretty much Waterman, except for this, instead of being an R and R prime, it's an R2. Just temporarily look at this. You see, this is in the left half of the cube, and it switches these two dedges. Now we observe our Waterman, which looks like it creates something ready to be fixed with PLL parity. It's in the right half of the cube, and I know we put in there at the beginning, but I had to do this R2. That's why I had to put it there in the beginning. I had to do this 3DW2 from the original Waterman because I had to do an R2 to make it look like this. With a setup move, it would create this. So it was a little bit of experimentation, but that's what I got. And that's the last bit of experimentation that's unobvious. From this point, it's pretty clear what needs to happen. So I promise that this is it. So in other words, I need to do a 3DW setup move to this to move most of the pieces that are affected into the left slice where the PLO parity affects them as well. Because I'm going to combine these two as one, and the PLO parity is going to switch this one with this one, so basically solve this switch center back here and move this black one back here. Very familiar stuff from what we saw in the previous video with the other type of 2-gen. Now quickly just erasing this and observing PLO parity, we can see that. And it's also, this rotates this 180 degrees, and so does our Waterman. Our Waterman also does the same thing. So I'm just going to combine them now, and I get this result here, which if I go to state, it's a 4 cycle with a 2-2 cycle of X centers, and that's the main combo. Now this and this is setup moves to this piece right here. This is the Waterman moved to one side of the cube so that we can apply this R2 move, and this is our PLL parity to solve back some pieces. So all this collectively together will make a 4 cycle of wing edges and a 2-2 cycle of X centers. Now to make a 4 cycle which doesn't discolor any centers, it may not be initially obvious, but whenever you try to make a brief move sequence, shifting should be your #1 tool. So if I just take PLL parity and I shift all of that to the beginning, then I have this setup right here that with if I just do an R and then I invert it, this was previously untouched. If I put that in here, red's going to swap with red. And there you go. This is a 4 cycle of wing edges that doesn't discolor any centers. And it so happens, and again, this is because I did this derivation ahead of time and experimented, but just based on this formation of the wing edges, because this is the case, this is the 3 cycle that we derived at the beginning that we used for the other algorithm. It cycles these wing edges right here. When you combine them together, it will create a 2 cycle. It's not the single dedge flip, but it's something along the lines of what we need.
Shift the last 11 moves to the beginning of the alg. Conjugate. Equals 55,37. Inverting all R moves and quarter turn 3DW moves to bring it to the front. Convert 3DW to 6DW to apply it to the 7x7x7 and to illustrate that it works on all big cube sizes.